Things they teach you in kindergarten. All right, so we spent last class going over homework, so we need to get back to the new topic. So 2 classes ago was a big day. So 2 classes back, we defined the term function and not just the term function and some important terminology that's related. So you need to go back to 2 lectures to sort of get that. And when I say things that were related, we talked about things like images and ranges and domains and codomains. And again, most of you have encountered these words before, but we're giving them a more precise meaning. And so we need to continue with that. And so here's a very important concept that we need to get into now. So this is something that maybe if you had a thorough pre-calculus instructor or a thorough maybe even calculus, well, I don't know. I mean, we really don't talk about it in Calculus 1 so much anymore. But there's an idea. One of the things you learn in algebra is this thing called an inverse function. And one of the things they teach you is that a function has an inverse provided it has this property, what we call it 1-to-1. And they really don't get too deep into this idea in algebra class, but what they usually tell you is they say there's this thing called the horizontal line test. Don't confuse it with the vertical line test, but the horizontal line test. And basically it says that a function has this thing called an inverse, which turns out to be very important. And the inverse exists provided there's this property called 1-to-1. And we need to understand that in advanced mathematics, this is a very important property of a function, so we're going to define it. So here's some new terms. So a function f is said to be, look at it, the old to be verb, which disappears in Pittsburgh, is said to be 1-to-1. That's a very common way of saying it. Or some people like to say the fancy word, injective, or an injunction, or no, what an injection, excuse me. So one way we might say it is 1-to-1, or we might say it's injective, if and only if f of A equals f of B implies A equals B for all A and B in the domain of F. What symbol? Right here? This? No, it's upside down A. This is for all. Remember this symbol? The existential quantifier, for all. Yeah, oh boy, you better get that in your brain before the exam. Uh-huh. So this is one way to define it. A logically equivalent way to define it is to say, okay, this sort of property here says if the outputs of 2 numbers are the same, or excuse me, let me be more clear. it says if I have two inputs and they give the same output, then the inputs have to be the same to begin with. That's what this is saying. So another way of saying this, so alternatively, we can say the following. If A is not equal to B, then f of A is not equal to f of B. So this is, again, we're getting into abstract things here. And a lot of times the first time you encounter these things, you guys, it's overwhelming. It's hard to learn. You got to remind yourself that you can do it. It just requires effort to understand this. So here's a famous example that you should keep in mind right away. Let's say f from, let's say, the integers into the integers given by f of n equals n squared is not 1 to 1. So oftentimes we'll abbreviate it with 1-1. Now, why is that the case? So well, let's see where the definition fails. Note that f of, say, -2 equals 4 and f of +2 equals 4. Well, this violates the definition. So all we needed to do was, notice the definition says for all A and B in the domain. If we want to negate that, all we have to do is give you one example, and we just did that. Now, here's an important thing to continue this example, and it should be very much understood. And the book probably does this example, so you should check it out in there as well. They might word it differently. Here's a thing to be very, very leery of. However, if we change the domain to f goes from the natural numbers into the natural numbers, it is 1 to 1. So let's see why. Let's go back to the red, and let's, of course, we want to ask why. Why? Well, what's the definition say? The definition says that we take two things and assume they're equal. So let's assume f of b equals f of a. That is, b squared equals a squared. Taking square roots, we have b equals a. Which is the definition of one-to-one. Now, if you are a curious student, you might say, well, why didn't you just do that argument before? Well, there's a subtlety that works here that doesn't work in the previous argument. Notice here I'm saying b squared is equal to a squared. The only reason it's logically true that b must be a is because I'm not allowing negative numbers. I can't take the square root of both sides and I can't go from b squared equals a squared and conclude that b equals a if I'm allowing b or a to be negative. We just saw that. If I'm allowing b and a to be negative, then -2 gives the same output as +2. Does everybody understand that? So there's a couple of very important things you need to consider here. Is to show something is not one-to-one, all I need to do is find one place where the definition is violated. And I did that. Now, it's not the only example. If I would have taken -n and +n for any n, it's violated. Now, if I want to claim something is one-to-one, I have to show that the definition is satisfied for arbitrary numbers. And I just did that. I just assumed that f of b equals f of a. Did I assume anything about a or b? No. By definition, then, the output is b squared, and the other one is a squared. And if those two things are equal, I can take square roots to conclude that b has to be equal to a. So these are, again, things that I hope you'll ponder. Now, you might be thinking, okay, why do we want to classify functions that have this property? Well, look at it. What's nice about this property, what you can clearly see in this example, is one-to-one means that you can't put two different inputs in and get the same output. And that is going to be the key idea to how we reverse the process of a function, or we talk about its inverse. So there is a connection between inverse and one-to-one. All right, here's another term. So we call f from, say, a to b onto or surjective if and only if for all b lowercase in the codomain, there exists a number little a in the domain with f of a equals b. So, and another way to write this property, so this means the range in codomain are the same. So to emphasize what we mean by this, and I hope you'll pay attention to this. So here's an example. If I take f from the integers to the integers, and let's say I say f of n equals n squared again, this guy is not onto. But if I say I'm going to go from the integers to the natural numbers, using the same rule, this is onto. Now, the best way with, I sound like a broken record, of course. The best way to get any of this to make sense is to do problems. And we will give you practice problems with this. Hopefully, you will be able to do them. And you will ask questions when you can't. That's the idea. Here's an important term. If f is both one-to-one and onto, we call f a bijection. Now, if f goes from, say, A to B is a bijection, we can define the inverse of f. So, okay, so how does the inverse work? What does that mean? You have some experience with this, but we want to go the opposite way. Like, we know that the inverse of x squared is the square root under the right context. We know that, for example, the inverse from calculus, the inverse of the natural log is the exponential function. So you recall how we denote this? We denote this by f with a sort of raised to the power -1. So what we write is, we write f inverse of b equals a when f of a equals b. So again, we're going sort of quick, and the reason we're going through this quick is these are all terms that are familiar with you. You've all seen these before. You might not remember them, and that's okay, but you should at least have some familiarity with these terms. Does anybody have a question, comment? All right, so let's do another familiar sort of idea, but we're going to define it officially now. Suppose f is a function from a to b. The graph of f. So you guys have been graphing for a long time now, but we're officially defining what is a graph. So the graph of f is the set a comma b, where little a comes from the set A, and f of a equals b. Now, if a and b are familiar sets like real numbers or integers, you can visualize the graph in the standard way, like you've been doing since you were in 7th or 8th grade. You make an XY axis, or you make some sort of visual. Does anybody have any questions about this? Comments? Now, one of the things you're going to have to get comfortable with, not just in this class, but for many of you in other math courses and also in classes in computer science, is you have to get comfortable working with functions that don't always remind you of the stuff you've used up through calculus. So we have to understand that what we've defined now give us generalizations of the concept of a function. And so it doesn't always just have to be f of x equals some formula. It can, but it doesn't have to be that way. There are lots of different types of functions out there, and we need to start becoming comfortable working with them. Does anybody have a comment or a question before we do some examples? You guys like examples, I know that. It's one thing I learned. Students love examples. Yeah.
It might not be related to this, but by saying that a function is one on one or one to one or whatever.
Yeah.
So does it mean it's always like either increasing or decreasing?
Okay, that's a good question. Is it always increasing or decreasing? So I don't know if you're thinking about that because of some things you might remember from calculus about a function is invertible if its derivative is always the same sign. But yeah, so the question was, does being one-to-one have something to do with increasing or decreasing? So one of your homework problems is going to be to actually show that. Now, the thing is the typical way you showed that in a calculus class is you would take the derivative, but we don't necessarily have the option to take a derivative here. Derivatives only make sense if the function we're dealing with is defined on a continuous interval or a continuum, as we will. And as we've seen through these examples, and as you can imagine in, say, computer science, oftentimes, and hence the whole point of this class, is discrete mathematics. It's where we're working not necessarily in what we call continuous math, which is like calculus and algebra. Now, we're worried about, okay, what if the function can only input positive integers? What if it can only output certain numbers where we don't have the luxury of being able to take derivatives? If a function is not defined on an interval, then the derivative doesn't even make sense. So the question is, and maybe we'll ask you to define this since we didn't state it, although we could have. So here was the question. Is one-to-one related to increasing and decreasing? And the answer is yes, in certain context. Now, I don't want to make it sound too crazy, but think about the notion of increasing and decreasing only makes sense if you have order, right? So if my function, if my domain or my codomain isn't necessarily numbers, right, then how can I have any order? How can I talk about something bigger than something else, right? So let's first understand that functions don't have to necessarily have a codomain and a domain be numbers. Now, if they are and they're real numbers, we know we can order them. Now, some of you might be familiar with the complex numbers. Maybe some of you seen them in another class, like, imaginary numbers and complex numbers. Turns out there's no order on them. So even the complex numbers, which are very important in lots of areas of mathematics and science and engineering, you can't even talk about necessarily increasing and decreasing there. But Abdullah, your question is a good one because it is related in a certain sense. It has to be, and we can write it down and we'll ask you to do it for homework. Here we go. So theorem, if f is strictly increasing or decreasing. Now, you'd have to remember what these things mean, and you can define them for yourself just to remember what increasing and decreasing means. Then f is one-to-one. Now, notice that this is an if-then. You might ask yourself, does it work the other way? Does one-to-one mean increasing or decreasing? And that's a good question I would ask you to think about. All right. So we'll let you think about that. That's a good question. What's that? Oh, I thought,
Really tall.
who was? Oh, we had a tall person walk past. So there you go, everybody. That's what you missed for not being here today. You
Extremely tall.
sure?
It looked like 7 foot.
All right. So here's a good example of what we might want to be able to do. Let's define f, and we'll say, look at this. This is going to look scary. We're going to say from the integers cross the integers. Remember what this means. So is it 1-to-1? Is it onto? So this is, for most of you have probably, I don't know that you've seen a function that looks like this yet. Unless you took Calculus 3 where we use more than one variable, most of you have not seen something described this way, so this is going to be overwhelming. What I would encourage you to do is think about, what does this mean? So this z with this little xz, what does that mean? We defined this before, right? It's called the Cartesian product. So what this tells us is we're not just inputting one number, we're inputting an ordered pair. An ordered pair is going into my function. And what my function does is it takes the first component of that ordered pair, and then it takes the second component of that ordered pair and it adds them together. So this function is well defined. You give it a pair of integers, it adds them together. So really, what is this function? This is a weird way of defining the operation of what? Addition. This is the operation of addition. Now you might say, this is weird, why would we do this? Well, think about it. Someone has to program a computer to add two numbers, right? So what someone does is that computer has a function. You give that computer two numbers, the computer takes those two numbers, and that program adds them together. Your calculator has a function built in like this. You give it two numbers, you hit equal, it spits out the sum of those two numbers. You understand what I'm saying here? So this is a perfectly valid function, and we want to know, is it 1-to-1, is it onto? God might know. Very well. Okay, so what do you do in these sense? You know, you have to get a feel for what's happening. Do you think it's 1-to-1? Do you think it's onto? Once you get an idea of what you think it is, how do you verify it either way? Logically. So how would I think about this? Well, the first thing I would do is ask myself, in words, what 1-to-1 means. The way I think about it, is it possible to get the same output for two different inputs? And it shouldn't take you long to figure out that that's the case here. So let me explain this real quickly. So here's what I ask myself. Is it possible to get the same output with two different inputs? And let me put these words in quotations because I'm kind of using them colloquially. I'm abusing the English language here. And so the answer to me, at least right away, is yes. And there's lots of examples. You know, f of, say, 2 comma negative 2 equals 0. F of negative 2 comma 2 equals 0. F of 5 comma negative 5 equals 0. F of negative 5 comma 5 equals 0. I mean, I can beat this dead horse all day. F of 2 comma 3 equals 5. F of 10 comma negative 5 equals 5, etc. There are lots of examples where two different inputs give the same output. And so that means, and really, we only needed one. We only need one example to contradict the definition. So we conclude F is not one-to-one.
Could you go back to the last slide for a few seconds?
Sure.
Thanks.
And if you have a question, let me know. And we'll go ponder the new slide, and then we'll let you, if you guys have questions, you can let me know.
Not
All
one.
right, I'm good.
Yes.
What do you mean? We said it's not one-to-one. Why would you want to answer yes?
No, yes to this question.
What
Is it
question?
possible to get the same output with two different inputs?
Well, that's the whole point. That's what I'm asking myself.
Yeah, so if we can answer yes to that
So yeah,
question,
if the
then it's
answer
not
yes,
one.
then it's not one-to-one. Correct. Does anybody have a question about this example? Remember, to show that it's not one-to-one, you just have to find one example that contradicts the definition. Now, the definition says that if the two outputs are the same, then it must be that the inputs were the same. Well, I just ruined that because here I got zeros. Here's an output of 0. Here's an output of 0, but the input here is not the same as here. And again, there was lots of examples I could use. Okay, so now the question is, how do we attack onto? So here's what I like to think about. For onto, here's what I ask myself. I say, self, does every element in the codomain have a partner in the domain. So basically we're saying, remember, that means that another way of thinking about being onto is that the codomain and the range are the same. Now the codomain here is the integers. So what I mean by this in the context of this problem, so in this problem, so given, I'll call it little z in the integers, can I find n and m in the integers such that n plus m equals z? That's what I'm asking myself in this particular problem. And of course, if you think about it, the answer is yes, but how do you sort of show that in general? Well, one way is to set n equal to 2 times z and m equal to z, or excuse me, negative z. Of course, there's other choices. Another choice is to set n equal to z and m equal to 0. That would work. And there's other choices that you could make. And so what we conclude then is we conclude that f is onto. Any questions or comments about this? Comments, questions? All right, so a special type of function that we'll spend some time with in here that many of you, not all, but many of you should be familiar with is the following. So a function f from the natural numbers to B where B is any set has a special name. It's called a sequence. So those of you who've had Calculus 2 or any math class where you've studied sequences, here you go. So in calculus, we usually introduce this as like a sequence is an ordered list, and that's really what it is. But in a more abstract way, we can think of it as a function that takes a natural number and maps it to some other element in a set. As many of you know, it's convention to denote the image f of n as a with a subscript n. And we give a name, so we call a sub n the nth term of the sequence. We often denote a sequence by a sub n with brackets like this. Sometimes we're very specific on what n represents. We might say n equals 1 to infinity, or we might even be a little more general and say that n starts at anything, not necessarily 1, where m equals 0, 1, 2, 3, etc. So again, we're introducing new notation to some of you. I understand that some of you are familiar with this, some of you aren't. Let's sort of give a couple examples that might be familiar to you or might help make these ideas a little easier to understand. Does anybody have a question or comment? All right, so let's just do a quick example or two. So here, let's say I'm going to do a sub n equals, let's say 1 over n. So what is this sequence? This sequence would be 1, 1/2, 1/3, 1/4, 1/5, etc. Now there's nothing special about using A. I can use any letter. So let's do the next one is B sub n. How about we do a slightly different one? How about we do -1 to the n plus 1. And so this sequence would be 1, negative 1, 1, negative 1, 1, negative 1. And that pattern continues forever and ever and ever. And then let's do one more. Maybe 1 over 2 to the power n, which is 1/2, 1/4, 1/8, 1/16, 1/32, 1/64. So you got to become familiar with this. Does anybody have a comment or question about these things? So once we have an ordered list, one of the things that arises and is often important to us is to add them, the terms. So we often need /want to add the terms of a sequence. So what we use is and this should be familiar to some of you, not all, so we use sigma or summation notation. So this is sort of a shorthand. All right. And that is, we say, okay, if I have a sub 1 plus a sub 2 plus a sub 3, and maybe I want to go up to, say, the 100th term, I can adopt the shorthand by saying, okay, we're going to take these terms and we'll start at the first and we'll go all the way up to 100. We don't always have to start at 1. Maybe we start at 0. Maybe we stop at some nth term. So again, these are shorthands that you as a student need to become familiar with. So again, some of you are comfortable with this already, some of you aren't. One thing I know as a student, when I was learning these sort of shorthand notations, it takes a while to get used to. Yes. It should be, yes, very good. This should be a 0 here. Thank you. So, by the way, the question was asked about the lectures. If you go to if you go to Canvas on a PC, it's going to be right on your front page. But if you're on mobile, it might be harder to find. Anyhow, we're past time. We got to get going. I will post some new homework. And please work on it over the weekend so that Monday we can answer any questions you guys have about any of this stuff. All right. I will see you guys on Monday, if not sooner. Thank you very much. If you have any questions, email me. Do not be shy. I will talk to you guys soon. Thank you very much.